Good morning, everyone, and thank you for being here. This session is Level 1 of our training path for Prolon and Neptronic applications. The purpose of this module is to build a shared practical foundation in HVAC systems, control sequences, electrical basics, and field signals. It is designed for sales engineers, technicians, and contractors because all three groups need the same basic language before moving into product-specific selection, setup, and commissioning. In other words, before we talk about specific controllers, actuators, valves, humidifiers, or heaters, we need to understand the system they serve, the logic behind it, the wiring path, and the field points that make it work. Welcome to Level 1 of the Training Foundation for Prolon and Neptronic applications. The objective of this session is to build the practical base that sales engineers, technicians, and contractors need before they move into product-specific selection, setup, and commissioning. At this level, we are not trying to make everyone a controls programmer. We are building a common language around HVAC systems, control sequences, electrical basics, and field signals. If someone understands what the equipment is trying to do, what the controller is looking at, and what outputs are being commanded, they will be much more effective in selling, advising, installing, and starting up these systems. This training matters because both Prolon and Neptronic are tied directly to real HVAC applications in the field. Prolon is strongly centered on configurable controllers for common HVAC equipment such as rooftop units, boilers, chillers, heat pumps, fan coils, and related systems. Neptronic goes beyond controls into actuators, valves, electric heaters, humidifiers, and other field devices. That means success with these product lines depends on understanding the mechanical application, not just the part number. A person may know how to wire a controller, but if they do not understand how the rooftop unit, humidifier, or valve is supposed to behave, they will struggle in the field. Level 1 closes that gap by giving everyone the same basic operating framework. To make that practical, let us use a constant volume packaged cooling-only unit, serving an office as an example, and follow the process from 1 to 4. First, know the equipment. This is a packaged rooftop unit whose job is to cool air and deliver a constant airflow to the office. Second, know the objective. The unit is trying to maintain the office at the required space temperature while providing the required ventilation. Third, know the logic at a high level. When the office is occupied, the unit fan must run. Cooling must be enabled when the space temperature rises above set point, and safeties must prevent operation if a required proof is missing. Fourth, know the field points. The controller may look at space temperature, discharge temperature, fan proof, and perhaps an outdoor air damper position, and it will command outputs such as fan enable, compressor stage 1, compressor stage 2, and economizer or damper output, if present. That simple example shows why application knowledge must come before product knowledge. Before anyone touches controls, they need to identify the equipment and the objective of that equipment. Every HVAC system is moving or conditioning something: air, water, refrigerant, or humidity. A rooftop unit is trying to condition and deliver air. A boiler is providing heat to a water loop. A chiller is removing heat from water. A humidifier is adding moisture. A valve is regulating water flow. An actuator is positioning a damper. If we want to simplify the entire controls field into one idea, it is this: controls exist to make the equipment achieve its intended process, objective. So the first question should always be, what is this equipment trying to control? and what field points tell us whether it is doing that correctly. A control sequence is simply the logic that determines how the system operates. In most HVAC applications, the sequence follows a recognizable pattern. First, the unit is enabled based on schedule, occupancy, or a command. Then the controller decides whether the unit needs heating, cooling, ventilation, or humidity control. After that, it stages or modulates outputs to meet the load. Throughout that process, it also checks safeties and proving conditions, and it generates alarms when something is outside expected operation. Many field problems happen because people see the system as a collection of wires instead of an ordered decision process. If you understand the sequence, you can predict what should happen next and troubleshoot much faster. Again, using a constant volume packaged cooling-only unit in an office, we can follow the 6 steps on this slide. 1. Enable. The unit is allowed to run because the office is in occupied mode by schedule or command. 2. Prove. The controller starts the supply fan and waits for a fan status proof or current switch to confirm airflow. 3. Compare. The controller compares the office space temperature or discharge temperature to the cooling set point. 4. Act. If cooling is required, the controller enables the first compressor stage, and if the temperature remains above set point, it may bring on a second stage. 5. Protect. The controller checks safeties such as fan-proof, freeze-a-stat if applicable, high-pressure or low-pressure trips from the unit, and short-cycle protection timers. 6. Alarm or fallback. If airflow proof is lost or a safety opens, the controller shuts down cooling as required, may keep or stop the fan depending on the sequence, and generates an alarm or fault condition. That is why sequence understanding makes troubleshooting more logical. It lets us ask where in the order the unit stopped behaving correctly. Before installation or startup, everyone must clearly understand the electrical distinction between line voltage and control voltage. Line voltage powers motors, heaters, and other high-energy devices. Control voltage is what the controller and most field logic circuits use to sense and command operation. One of the most common causes of field damage is confusion between the two. Beyond voltage levels, the team must understand transformer paths, commons, interlocks, safeties, relay logic, and the difference between powering a device and commanding a device. A startup should never begin until the electrical path is understood. Safe and disciplined electrical verification is not optional. It is a core part of successful commissioning. To stress the most important point on this slide, remember that electrical troubleshooting starts with clarity on the path, not with guessing at the controller. On a CV-packaged office unit, for example, line voltage may feed the supply fan motor and compressors, while 24-volt control power feeds the controller, thermostat, or sensor circuit, relays, and safeties. If the transformer's secondary, common, or safety chain is open, the equipment may have power available and still not operate correctly. That is why the team must verify the transformer path, identify the common reference, and confirm each interlock and safety before startup. Many apparent control failures are really wiring, common, or safety chain problems. This slide introduces the field devices that make the system real. Sensors tell the controller what is happening. They may measure temperature, humidity, pressure, current, airflow, CO2, or water temperature. Actuators and valves are final control elements. They physically change the process by opening a valve, moving a damper, or adjusting airflow or water flow. The controller is constantly making decisions based on what sensors are reporting, and then issuing commands to outputs that affect the process. A good way to explain this is, inputs describe the condition, outputs change the condition. When people understand that relationship, they begin to see how the entire control loop works. Inputs report, outputs act. At this point, we connect field devices to controller language. Inputs and outputs are usually classified as analog or digital. Analog means the value varies across a range, such as temperature, humidity, pressure, or a modulating command like 0 to 10 volts to a valve actuator. Digital means the signal has two states, such as on or off, open or closed, normal or alarm. This gives us AI, AO, DI, and DO, analog input, analog output, digital input, and digital output. A technician who can identify the point type, signal range, and expected device behavior will troubleshoot much faster. A sales engineer who understands these point types will also be better at reading sequences and matching products to the application. Here are practical examples. In a constant volume packaged cooling-only unit serving an office, the space temperature sensor is typically an analog input because the controller is reading a changing temperature value. The fan status proof is typically a digital input because it is either proven or not proven. The fan enable relay is typically a digital output because the controller is commanding the fan on or off. If the unit has an economizer damper with a modulating actuator, the damper command is typically an analog output because the controller may send a varying signal such as 0 to 10 volts. In a chilled water air handler application, chilled water supply temperature can be an analog input. A chilled water control valve command can be an analog output. A freezostat can be a digital input, and a pump enable can be a digital output. In a VFD supply fan application, the VFD speed command is usually an analog output, while the run command is digital. These examples help the audience connect AI, AO, DI, and DO to real equipment behavior in the field. Now, we put everything together in one practical example. In this rooftop unit application, the system may include cooling, outdoor air economizer control, electric reheat, and humidity management. To understand this application, the audience should ask 4 questions. First, what is the equipment trying to maintain? Usually space conditions or discharge conditions. Second, what sensors tell the controller what is happening? Third, what outputs can the controller command? And fourth, what safeties or interlocks can prevent normal operation? In a case like this, the controller may decide when to bring in outdoor air, when to call for cooling, when to energize reheat, and when to manage humidity. This is a good example because it shows that field success depends on combining equipment understanding, sequence logic, wiring knowledge, and point mapping. Let us walk through the example from sensor input to humidity output. The sensor inputs may include space temperature, discharge temperature, space humidity, and fan proof. Those inputs tell the controller whether the space is too warm, too cold, too humid, or operating without proven airflow. The controller logic then decides whether the unit is in occupied mode, whether cooling is needed, whether economizer cooling is available, whether electric reheat is needed to maintain discharge or space conditions, and whether humidity control should be enabled. On the airside outputs, the controller may enable the supply fan and modulate the outdoor air or economizer damper. On the heat output side, it may command staged or modulating electric reheat through a relay, SSR, or SCR, depending on the design. On the humidity output side, it may enable a humidifier, provided that the required safeties such as airflow proof and high limit protection are satisfied. This example is important because every step depends on the one before it. If the fan proof fails, electric heat and humidification should not be allowed to operate. If the sensor values are not believable, the controller decisions will be wrong. And if the outputs are commanded but the physical device does not respond, the process will not stabilize. This is exactly why we say a practical application combines equipment knowledge, sequence logic, wiring discipline, and point mapping. Just to clarify, SSR, solid-state relay. An SSR is an electronic relay with no mechanical contacts. It uses semiconductor components to switch a load on/off based on a control signal. Typical use: 1. Turning electric heaters on/off. 2. Switching humidifiers, small motors, contactors, or resistive loads. 3. Replacing mechanical relays/contactors where silent operation and longer life are desired. Typical control signal: 24 volts AC, 24 volts DC, 0 to 10 volts DC, depending on model. Key point: SSR is mainly an electronic on-off switch. Example: a controller sends a signal to the SSR, and the SSR energizes an electric duct heater stage. SCR, silicon-controlled rectifier. An SCR is a semiconductor device used to control how much power is delivered to a load by adjusting the AC waveform. In HVAC, when people say SCR controller, they usually mean a modulating power controller using SCR technology. Typical use: 1. Modulating electric duct heaters. 2. Precise temperature control. 3. Electric heating coils where proportional control is needed instead of simple staged on-off. Typical control signal: 0 to 10 volts DC, 2 to 10 volts DC, 4 to 20 milliamperes. Key point: SCR provides proportional/modulating control of power, not just on/off. Example: a controller sends a 0 to 10 volts DC signal to the SCR. At 5 volts DC, the SCR may deliver approximately 50% heating capacity. At 10 volts DC, it delivers 100%. A successful startup is never random. It should follow a disciplined checklist. Before power-up, the installer should verify device mounting, wiring separation, sensor placement, safeties, and labeling. At initial power-up, the team should confirm power quality, controller status, and basic input reading. After that comes functional verification, proving that each input is believable and each output produces the expected field response. The important message here is that commissioning begins with verification, not with changing set points or guessing. A structured process prevents wasted time and reduces damage risk. This mindset is especially important when working with controls, humidification, electric heat, valves, and integrated HVAC applications. To clarify the term, commissioning means the systematic process of verifying and documenting that the installed system is designed, installed, tested, and operating as intended. In practical terms, commissioning means checking the installation, confirming the wiring, proving the safeties and interlocks, validating the inputs, testing the outputs, observing the physical response of the equipment, verifying sequence operation, and documenting the final settings and results. The key steps usually include pre-startup inspection, initial power-up, point-to-point verification, functional testing, safety testing, sequence validation, adjustment if needed, and final documentation. The benefits are significant: better safety, fewer callbacks, faster troubleshooting, better comfort and performance, less equipment damage, and a clearer handoff to the owner or service team. Commissioning is not just starting the unit, it is proving that the full application works correctly and safely. By the end of Level 1, the learner should be able to identify the main HVAC applications addressed by these product families, explain the basic operating order of a control sequence, distinguish power wiring from control wiring, recognize common field devices, understand analog and digital I/O, and perform a structured basic startup verification. This does not mean they are finished learning. It means they now have the foundation required for Level 2, where training becomes more product-specific. Once this base is in place, it becomes much easier to learn controller families, set up tools, selection rules, and advanced commissioning workflows. Level 1 gives them the operating framework. Level 2 will teach them how each product family is applied within that framework. Thank you for your time and attention. Level 1 is about building the common language of HVAC controls and field devices. Once everyone understands the application, the sequence, the wiring path, and the point types, the product training becomes much more effective and much more practical. From here, the next step is Level 2, where we move into product families, application fit, and product-specific workflows.